Let's now talk about decision matrices and error correcting output codes. So when we are dealing with multi-class classification with Ensemble, there is, I would say, an interesting modeling based on weighted vote that allow to, I would say, adjust the vote according to the models, the basic members of the ensemble and the classes. And as such, we have a decision matrix that encode the weights Wij. So Wij basically mean that we are dealing with class I because we are looking at HI bar. So basically the decision for class I for classifier J. So this weight allowed to give the value for decision from classifier J for class I. And as such, we can build a decision matrix for different cases. An example for the one against all classification that we saw in some weeks ago in the case of linear classifiers, how to make these binary classifiers to be usable in a multi-class setting. For the one against all classification, an example here with 4 classes and as such 4 models is to say that each row here, each column here is for a classifier. So we have 4 classifiers that way. And we have 4 rows that correspond to each classes. So the classifier 1 is assigning the class 1 to positive and the 3 other classes 2, 3, 4 to negative. And likewise, classifier 3 here is assigning, so this is classifier 3 for class 3. And as such, it assigns samples to the positive for class 3 and negative for class 1, 2, and 4. So this is how we can interpret that matrix, and that's relatively straightforward. The point here, however, and this is the case for one against all classification, is there will be some ambiguity when a basic classifier makes a bad decision, because there is likely to be 2 values of H bar equal to 0 for a given 2 different indices. That can happen. That it will in fact be very likely to happen here when we are making a bad decision, and then it's not easy to resolve that, and usually we get in a case where we will need to reject or not process with that ensemble the sample at end. And an issue with that model, if we look at the decision matrix, and this is a basic idea with decision matrix, is that we are looking at the similarity between codes. And as such, we call this the Hamming distance. We want a low Hamming distance. Hamming distance is basically a distance measure between vectors of bits. For example, we are looking at for 2 vectors of the same size, the differences at each position between the bits of the 2 bit strings. So if they are 1, 1, that's okay. There's no difference. If it's 0, 1 or 1, 0, or here we are working with +1, -1. If it is +1, -1, there are a distance of 1 that is added. So if we have many features like that, not features, but many, I would say, elements that we are comparing like that over the classes, there will be, I would say, an higher Hamming distance. It takes more modification to reach to the same values. So here we have an example of another case for multi-class classification, that is 1 versus 1 decisions. So we are making a case here again with 4 classes, and that requires, in fact, 6 different models to get all the combinations of decision pairs. And here we just deal with the first half in the sense that we are dealing with classifier 1 versus classifier 3. So we have it here in the second column. For example, it's 1 versus 3. We don't do the other way of 3 versus 1. We don't do like here it's +1, 0, -1, 0. We don't do the -1, 0, +1, 0. This is redundant. But so as such, the number of different pairs we can deal with are 6 here. So we have like 1 versus 2, 1 versus 3, 2, 3, 4, 3, 4. So these are like different cases, and 1, 4, and 2, 4. So these are the different comparisons we are making. So we have all the 6 pairs. here that are dealt with. And with the weight of 0, it means that the decision is ignored. We are basically trying to disable the effect of that pair over that sample. And the error in one basic classifier may or may not imply ambiguity. So it could be ambiguous. We can get into a decision where there is no one top class HI bar. There are like 2 of these values that are equal for 2 different classes. So that's possible, but at the same time, it's also possible that we've got, even with one model that is making a mistake, a correct decision. And the point here is that the value of L, the number of members in the ensemble, grow quadratically with K, which is unsustainable if we have, I would say, 100 of classes, which is something that can happen. So it can only be applied for like small number of classes for like the 1 versus 1. And then we can generalize this into a third approach that is called the error correcting output codes. Then we just preset some size and we build a decision matrix rather arbitrarily, but based on some principle. And then this basic principle is to try to maximize the Hamming distance between each line. So all the combination of lines here, we have 3 of them. We have 1 versus 2, 1 versus 3, 1 versus 4. So we have like 3 of those lines that can be compared. No, there's more than that. So it's in fact it's 1, 2, 1, 2, 1, 3, 1, 4. But we also have 2, 3, 2, 4, 3, 4. So we have 6 combination of 6 pairs of classes like we do have in the 1 versus 1. But now we are looking at the Hamming distance between each of these pairs. So with K classes, in fact, if we were looking to enumerate all possibilities, it will be huge for K that is, I would say, over a few value of a few classes. So there is like 2 power K minus 1 problems with 2 different classes. That's too big. And we don't want to deal with that. It's not necessarily interesting. What we want to do is to get a diversity of discriminants, and we want them to be specialized on different subset of classes. Because here in that approach, and like with the other approaches, we are still dealing with binary classifiers like linear discriminant or SVM. And the idea is that they are dealing with false classes. We are building, in fact, subset of classes as the positive class, and the rest of the other classes are made in the, I would say, the negative meta class for that model. So we want that to be diverse, and so we specialize them on different classes. And the idea with error correcting output codes is that we will build this in order to increase the Hamming distance, and we want the different components for a line. An example here, and which is one possible case among many others that will be satisfying this idea of maximizing the Hamming distance, is this thing. So we have 4 classes and we have 9 classifiers. This number is arbitrary, but that's, I would say, good to illustrate here. So we see that each line is for a class, each column is for a classifier. So we have, in the first case, 4 positive versus 1, 2, 3 as negative. The second one is 3 positive, 1, 2, 4 as negative, and so on. Another further away, we have this. It's kind of inverse. We have like 1 as -1, and the 3 others, 2, 3, 4 as +1. But we have other cases which are more mixed. I would say 1 and 3 versus 2 and 4 here. So these are all different cases. You can see, however, in the construction, there are some patterns in terms of building the thing. So it's basically like this 1, 2, 3, 4, 5, 6, 7, 8. So yeah, 8, 9, or maybe not 8. Anyway, the point here is that we are building this thing with some kind of patterns, but it's one possibility among many others, and usually an heuristic is used to build that thing. So we want we are looking at the minimum difference, the minimum Hamming distance, which is d equal to 5 between each pair of lines. So given that the minimum Hamming distance between the 6 pairs of classifier is 5, And if we apply just the formula here, forming distance, it means that we are looking at this distance d equal to 5 minus 1 divided by 2, and we just round down floor. So here we have like 5 minus 2 divided by 2, which is equal to 2. That means that we can make up to 2 basic classifier errors with that specific ensemble built with that matrix. And then we choose the class according to the H bar that is maximum over all the 4 classes. And if we are able to normalize this in 0, 1, which can be the case because we have a limited number of vectors, so we know what is the maximum and minimum values. If we renormalize everything between 0, 1, we can consider to use a probabilistic interpretation of the output for each class. So, like I say, the matrix W here is partly arbitrary. There is some, I would say, patterns into that, but there's basically it's something that we often do manually with some basic algorithms.